Hello guys, how are you today? So today I'll be explaining the physics AMS of term 2 week 10. So let's start with the first question. A rectangular wire ABCD is connected to a galvanometer that measures induced electromagnetic force. The wire is rotated at a constant rate inside a horseshoe magnet as shown below. How could we possibly increase this electromagnetic force in the wire? Very simply, you have many ways. Either it is to increase the magnetic field, and remember, magnetic field is denoted by B, okay? Or you could increase the speed of rotation, or you could increase the length of the wire, or you could increase the angle of rotation. So the more rotated it is, the more the electromagnetic force could enter the wire, and use multiple loops. These are just some of the possible values, not values, my bad, some of the possible options that we could put. So to increase the electromagnetic force in the wire, you could use multiple loops, you could increase the angle of rotation, you could increase the magnetic field denoted by B or beta. You could increase the speed of rotation, and you could increase the length of the wire. So definitely over here, by rotating the wire faster is the correct answer. We move on to question number 2. A loop ABCD is rotating between the poles of a permanent magnet. As you can see over here, this is rotating. This is its sign. So if they did not tell you rotating, but you saw the sign in the exam, that means it is rotating. Now, if it is rotating, that means it is an AC current or an alternating current. Okay, and what about the alternating current? We know that the alternating current, okay, it will change every half rotation. So the alternating current, it will turn like this, then it will turn again like this, and then like this, and etc. It will switch, or it will change its direction of rotation every half rotation. And yeah, this is pretty much about the rotation. Another thing is that the magnetic field. What about the magnetic field? We know that the magnetic field outside goes from the North Pole to the South Pole. And as you can see, it is perpendicular to the wire. So when it is perpendicular to the wire, in this case, it is horizontal. So horizontal means it's perpendicular, or the wire is perpendicular to the magnetic field, and the wire is being horizontal in this case. That means it has what? It has a change in magnetic flux. Magnetic flux is denoted by phi. It is equal to 0. However, if it were vertical, if it were standing like this, I don't know how to draw it, just bear with me. If it was standing like this, if it was standing vertical, and the electromagnetic field is passing through it, that means it is not perpendicular to it. In another term, it is parallel to the wire. So yes, then the change in magnetic flux is gonna be maximal or maximum. So let us read the options. The current through the galvanometer changes its direction twice every complete rotation. Okay, so the current through the galvanometer changes its direction twice every complete rotation. We said that the current will change its direction every half rotation. So one current, we'll make it an equation. It will be a little bit of math. So one current is equal to half a rotation. Okay, what about a complete rotation? So one rotation, one full rotation, that means the current is equal to 2, because you are multiplying it by 2. So definitely this is correct, because the current changes its direction twice every complete rotation, or in another term, the current will change its direction every half rotation. The frequency of the generated current is double the frequency of the loop's rotation. Here what they are saying is one current is equal to 2 rotation, which is not the case. We said that actually it's the opposite. 2 current is equal to 1 rotation. So this is definitely wrong. The current in AB CD is called an alternating current. This is true because it is switching the current every 180 degrees or every half rotation. Again, we said if ABCD is vertical, that means the magnetic field is going to be parallel to it, then the current through the loop is going to be maximal. Whereas since it's horizontal, the rate of flux change or the electromagnetic force through the loop is going to be 0. So again, remember, if the magnetic field is perpendicular to the wire, so let us say this is magnetic field M and this is wire W. If they are perpendicular, then they have 0 change in magnetic flux or current. However, if they are parallel to each other, if this is the magnetic field and this is the wire, then you will have maximum change in magnetic field and current. So you're going to have maximum current and maximum rate of flux change through the loop. So these are actually the only 3 answers we have for question number 2. Let us move on to question number 3. 2 insulated wires were welded together as shown in the diagram below. As you can see, you have one wire is going down a little bit, the other wire is going up. So as you can see, I think they're both live wires. Which of the following is most likely to happen? As you can see, some of the wire is going to be able to flow through the plastic case. Okay, so we call this what? A leakage. This is a leakage of electric flow or a leakage of electric current. Now, what exactly happens here? When there's a leakage of electric flow, the current is going to turn on and off. Then there is going to be a fire. A fire is going to happen because of the leakage of electric flow. Okay, because why? A lot of the energy is going to be lost as heat, and all of this heat is going to cause a fire, and due to the fire, the wire case is going to melt. And if a person was to touch the plastic case, they were to get electrocuted, but here in this case, they did not say that the person is touching the plastic case, so he's not going to get electrocuted. So, first of all, a fire goes off. Why does the fire go off? Because a current goes on and off, and because of this fire, the wire case is going to melt. We move on to question number 4. A coil is rotated in the presence of an external magnetic field to produce electricity. The output voltage generated in the coil is shown below. They said if the surface of the coil or the wire is perpendicular, remember perpendicular means 0 or like no magnetic flux and no current. So 0 magnetic flux and 0 current. Whereas if it is parallel, you're going to have a maximum magnetic flux and maximum current. So here in this case, if it's perpendicular, it's going to have 0. So you're going to take the points and write it as 0. It's usually these points. This does not have a notation, so you're going to take it as A and C. Okay? Now, for the second one, they need when it's parallel. That means we're going to have maximum. Maximum can be in both directions. Either upwards being B or downwards being D. Okay, so the magnetic field is gonna be maximal when it is parallel. The magnetic flux is gonna be maximum when it is parallel to the surface of the coil. In this case, you're gonna choose the maximum point up and the maximum point down. We call these the extremes or the crests, okay? So in this case, it's gonna be B and D. We move on to question number 5. This question is a new question. A coil of wire of area 0.09 meter squared is placed in the perpendicular magnetic field of magnitude 0.5 T. T, this is the magnetic field, okay? Magnitude. The magnetic field uniformly increases to 0.6 T in 3 seconds. So let us first of all write down everything we have. We are given area, okay? We are given magnetic field initial. We're given magnetic field final, and we are given the difference in time, delta T. Now what we need to know is that the electromagnetic force, EMF, it is equal to what? It is equal to minus the change in magnetic flux over the change in time. according to Faraday's law, the electromagnetic force is equal to the opposite of the change in magnetic flux over the change in time. Okay, so magnetic flux is what? If you remember from previous exams or previous AMS quiz, magnetic flux is equal to the magnetic field times the surface area. Now, do they need the electromagnetic force or the magnitude of the electromagnetic force? They need the magnitude, so we're going to be putting it in absolute value with the minus, of course, so it's going to be like this. And so then the new equation looks like this. The magnitude of the electromagnetic force is equal to the change in magnetic flux over the change in time. Of course, the surface area is not going to change, it's going to stay the same. So change in electromagnetic force is equal to the area multiplied by the change in the magnetic field over the change in time. Now all we need to do is substitute our answers. So our area in this case, it is 0. Let me find the space. It is 0.09 meter squared times the change in magnetic field. So it's going to be 0.6 minus 0.5, which is 0.1, over the change in time, which is 3 seconds. If you put it on your calculator, you are going to get 3 times 10 to the power of minus 3. But do they need it in volts or in millivolts? They need it in millivolts. So to make it into millivolts, we will multiply it by 10 to the power of 3. So we will get an answer of 3 millivolts. This is our answer for question number 5. We move on to question number 6. This is a very simple question. Now what we need to know about transformers. Okay, we have a transformer over here. Let us say it is a step-down transformer. It will look like this. Okay, of course we have a primary voltage, so V1, secondary voltage V2, and we have the number of turns 1 and the number of turns 2. And usually in between them we have 2 lines, and this is soft iron. Okay, now what about the magnetic field? What's gonna happen is that in the primary, not the magnetic field, sorry, in the transformer, in the primary coil, which is N1 and V1, which is this coil over here, it will generate an alternating current. And remember, the graph of the alternating current is a sinusoidal graph. It looks like a sine function. So it will generate an alternating current that will pass through the wire. And remember, if you have a current that is moving around the wire, it will create a magnetic field. Now, because there is a magnetic field and we placed soft iron in between, what's going to happen is that the soft iron is going to deflect or redirect the magnetic field. And so it's going to go into N2, the second wire. And this will create an electromotive force, which is the second voltage. If it's a step down, then definitely it's going to create a smaller electromotive force. So that means the soft iron core will help in linking the magnetic field of the primary coil with the secondary coil. The primary coil will generate an alternating current, and the secondary coil will induce an electromotive force. We move on to question number 7. Here we have to pay attention. They said, in order to decrease losses of energy in power transmission from power plant through the grid, certain measures must be taken. What about these measures? The amount of loss of energy in the wire. It is power. Okay, remember, it is power. It is equal to the square, or not equal, sorry, it is proportional to the square of what in the wire? We know power is, first of all, equal to current times voltage. Another equation is voltage squared over resistance. And another equation is current squared times resistance. If it is directly proportional, that means they have to be on the same side, or like it is all multiplication on the other side. So that is why we are going to take this one and not this one, because here it is the denominator, and because there is division and R, the resistance, is our constant value, okay, then we cannot apply this rule, because the power, or the amount of energy lost, it is directly proportional to the resistance, because resistance is our constant value. So if it's going to be directly proportional, then it's going to be directly proportional to the square of the current, because they are on the same side. So it is directly proportional to the square of the current in the wire. Now, in order to decrease these losses, okay, in order to decrease the loss of energy as heat, we use step-up transformers because they increase the voltage. So when they increase the voltage, what is gonna happen? We are gonna decrease the current because remember, in transformers, we have a couple of equations, yeah? We have equation N2 over N1, V2 over V1, I1 over I2. As you can see, the only thing that is different is I1 over I2. So they are opposite. So if you use a step-up transformer and you increase the voltage, what's going to happen to the current is that it's going to decrease. So very simply, if you have a low current, as we stated above, having a low current is going to cause a less amount of energy lost. So that is why we need a higher voltage. So very simply, as a result, the grid transports the electricity at a high voltage and a low current. So let us move on to question number 8. A transformer has 60 turns in the primary coil and N turns in the secondary coil. The peak electromotive force in the primary and secondary coils of the transformer are 48 voltage and 240 voltage respectively. They need us to find the number of turns in the secondary coil. We know that in the primary coil it has 60 turns and we have the primary voltage and secondary voltage. So what we're going to do is we're going to apply the equation N2 over N1 is equal to V2 over V1. N2 is what we need to find over N1, which is 60, is equal to V2, which is 240 over V1, which is 48. You do cross multiplication, you are gonna get 240 times 60 divided by 48, which is then equal to 300. So the number of turns in the secondary coil is 300 turns. The current in the primary coil is 4 amperes and the current in the secondary coil is 0.72 amperes. So what do we have? Over here we have I1 and I2. They need the input power of the transformer. We know that voltage 1 is 48 volts. Voltage 2 is 240 volts. Okay, the input power 1 is equal to I1 times V1. So very simply it's equal to 4 times 48, which is then 192 watts. For P2, which is the output power, it is very simply I2 times V2. So I2 it is 0.72 and V2 it is 240 volts. So very simply 0.72 times 240 volts, you are gonna get an answer of 172.8, rounded 173 watts. So very simply, here it is 192 watts, here it is 173 watts. Now they need the efficiency. The equation of efficiency is power 2 over power 1 times 100. So 173 over 192 times 100. Put it on the calculator. You are gonna get an answer of approximately 90%. We move on to question number 9. Here, this is a question we haven't taken before. And even my teacher was surprised to see something like this. But no worries, she gave me the equation and I will explain to you how to solve this. First of all, an alternating current is given by the expression I is equal to 45 milliamperes times sine 18.8 radius blah blah blah, whatever you pi as 3.14. Alternating current has a sinusoidal or like a sine function. It has a graph which is sinusoidal or in a sine function manner. Let me just do it properly, like this. Okay, something like this. I'm not the best at drawing, but you can understand what I mean, yeah? So, they're asking us for the peak value of the current. Always the peak value of the current is this number over here, so it's gonna be 45 milliamperes. Now the frequency. To find the frequency of this current, we know that it is written like this: 45 milliamperes times sine 18.8 times what? Times radian, or I don't know what this is, a rad. It could be radical, it could be radian, I don't know what it is. Times the speed inverse times the time. Now here this is something important. Anytime you see something multiplied by the time, this number inside the sign, which is 18.8, it is going to be equal to 2 times pi times the frequency f. So to find the value of the frequency f, first of all, you're going to use pi as 3.14. Okay, so to find the value of the frequency f, it is 18.8 over 2 times 3.14 is equal to f. Put it on the calculator. You are going to get an answer of 2.99. You can put it like this, or you can round it and you can put 3 as your answer. So for the first one, it is 45, and for the second one, it is 3 hertz. We move on to question number 10. They need us to find the efficiency of the transformer. Very simply, efficiency is power 2 over power 1 times 100%. Here we have a small issue in that we have everything in amperes and voltage, and this is only in milliamperes. So to change it from milliamperes to amperes, we're going to multiply it by 10 to the power of minus 3. So secondary coil, which is power 2, to find its power, it is going to be 162 times 10 to the power of minus 3 times 110 volts. And then power 1, it's very simply 2.2 times 9. Put it on the calculator. 162 times 10 to the power of minus 3 times 110, okay, over 2.2 times 9, and you're gonna be having what? You're gonna be having power 2 over power 1, and you will get 0.9. But we do not stop here. We're gonna do 0.9 times 100%, and you're gonna get then 90%. Okay, this is it for this question. We will move on to question number 11. This is a simple question. If a transformer had 760 turns and then it decreased to 100 turns, this is a step down transformer. You denote it by step dash down or step space down, whatever is fine. We move on to question number 12. If the secondary coil has more turns than the primary coil, then this is a step up transformer. It's denoted by step dash up transformer. So very simply, if the secondary coil has more turns than the primary, it is step up. You can denote it step dash up. And if the primary has more than the secondary, then it is step down or step dash down. We move on to question number 13. When the transformation ratio is less than 1, the transformer is called a step dash down transformer. Why is that? Because the transformation ratio, okay, it is usually what? It is N2 over N1, or it is V2 over V1. So if this ratio is less than 1, that means N2 is less than N1, and that means that N2 has less turns than N1. That means it is a step down transformer. We move on to question number 14. They told us an ideal transformer has primary and secondary coils of 160 and 4,800 turns respectively. The AC voltage at the output of the secondary coil is 270 volts. They need the voltage connected to the input of the transformer. Very simply, the primary coil N1 is 160, secondary coil N2 is 4,800, and then secondary voltage V2 is 270. So it's gonna be N2 over N1 is equal to V2 over V1. So 4,800 over 270, not 270, oh my goodness, my bad, over 160 is equal to 270 over V1, which we can denote as X. You can do cross multiplication. You will get 160 times 270 over 4,800, which will give us 9 volts. So very simply, the answer over here is 9 volts. We move on to question number 15. The input voltage in the ideal transformer is 12 volts. The number of turns in the primary coil is 100 turns. The number of turns in the secondary coil is 650 turns. So V1 is 12, N1 is 100, N2 is 650. They need the output voltage, which is V2. Very simply, we will follow the equation. V2 over V1 is equal to N2 over N1. So it's 650 N2 over N1, which is 100, it is equal to V2, which is V2, over V1, which is 12. So now you do cross multiplication. You get 650 times 12 over 100, and you are going to get 78. So V2 is equal to 78 volts. We move on to part B. I don't know what undefined is for, just ignore it. Based on the number of turns of the transformer is A. So based on the number of turns, as you can see from the number of turns, it was 100 and then it became 650. So it is a step up because definitely the number of turns increased, so it's a step up transformer. We move on to question number 16. A transformer has 300 turns in the primary coil and 500 turns in the secondary coil. The current in the primary coil is 5 milliamperes and that in the secondary coil is 27 milliamperes. Okay, what we need to know, first of all, is that the equations are N2 over N1 is equal to V2 over V1 is equal to I1 over I2. So, very simply, just keep this in mind while we are solving. A transformer has 300 turns in the primary, so N1 is equal to 300. N2 is equal to 50 turns. We don't have N again. We have I1 being 5 milliamperes, and then I2 being 27 milliamperes. They need the efficiency of the transformer. We know efficiency is power 2 over power 1 times 100%. So how do we find power in general? Power is equal to the current I times the voltage V. If you look, we do not have the voltage. So what we could do, we could play it smart. We know that we have N2 being 50 and N1 being 300. So it's going to be equal to V2, which is voltage 2 over V1. So very simply, what we could do is we could take them as substitutes. So V2 is 50 and V1 is 300. Okay? So now, to find power 2, first of all, it's going to be 27 milliamperes multiplied by the voltage 2, which is 50. Power 1, it is going to be, very simply, 5 milliamperes multiplied by 300. Okay? So you're going to put them on top of each other. It becomes 27 milliamperes, or just 27 times 50 over 5 times 300. And you are going to get 0.9. But don't forget, you still need to multiply it by 100 to get 90%. So 90%. Now, based on the number of turns, if it was initially 300 and it became 50, it's decreasing. So it is a step dash down transformer. We move on to question number 17. A step-up transformer, definitely it will increase the voltage because, as you know, N2 over N1 equals V2 over V1. So if it's a step up, that means N2 is greater than N1. That means V2 is going to be greater than V1. An ideal transformer has 100% efficiency. If it has 100% efficiency, that means power 2 and power 1 is equal to 1. So power 2 over power 1 is equal to 1. And if they are equal to 1, that means they are the same. So it will not change the output power. However, a real transformer can never be 100% efficient. That's why a real transformer always decreases the output power. That's why power 2 is always less than power 1. Okay? If a transformer increases the output voltage means voltage 2 will increase. So voltage 2 over voltage 1, voltage 2 increases. That means what's going to happen is that the current, on the other hand, because it is flipped, it's going to have an opposite effect. So it is going to decrease. So it will decrease the output current. So we move on to the next question, which is question number 18. Here you just need to memorize that the maximum voltage you could have is a supergrid. The minimum or lowest voltage you could have is a power station. Then after supergrid you have a grid, and then after the grid you have heavy industry. So remember, from least voltage to highest voltage is power station output, heavy industry, grid, and supergrid. We move on to question number 19. An electric heater is labeled 240 volts, 50 hertz, 2000 watts. The label also states the appliance must be earth. Earth means you connect a wire to earth, and the electric the electric buildup will flow to earth instead of on the object. Okay, now the part of the heater that must be earth. Definitely, the thing that must be earth is the thing that we are gonna touch. So, the socket. Do we touch the socket when we're dealing with the appliance? Definitely not. When we're dealing with an electric heater, we do not touch the socket because we know that it is gonna be dangerous. And anyways, the socket needs to have an electric buildup so it can power the appliance. Same thing with the electronic chips. They need an electric buildup. Same thing with the resistors. Actually, resistors don't need to be earth because they block the electric flow. Okay, and finally the heating element, it needs to be heated, so it needs the electric buildup on it. So definitely the only thing that does not need the electric buildup on it that we need to earth is the case. Okay, the heater contains a standard electric fuse. The fuse is placed on the live wire. Why is it placed on the live wire? Because the live wire has the current passing through it. And what is the fuse's role? When a current greater than the needed current will pass through the fuse, it will melt and it will disconnect and not let the current to flow through and damage the current. So now we need to find which fuse that we could possibly use. Let us find first of all the current. To find the current, in this case, it is going to be power over voltage. So the power is 2000 over the voltage, which is 240. So it's going to be approximately 8.333. Now, you will not choose anything that is way too small or anything that is way too big. Yani, in this case, the lowest you could choose is 8. And the highest you could choose, it can be as high as possible, but يعني, it has to be as close as, يعني, if it's, for example, 8.33, the lowest you could ever go is 8. You cannot go less than this unless it is needed to, because if you choose less than it, it's not gonna work. It needs minimum 8 for it to function. It needs a minimum current of 8 amperes for it to function. Whereas if you choose a fuse that's, let's say, 13, which is the answer in this case, okay, the wire, the current is gonna flow through it, the current is gonna pass through it, but at some point, if it's a greater current than needed, then the device is gonna be damaged. That's why it's more preferable to choose a little bit less, okay? يعني 8.33, choose 8. That would be more, يعني, up to what we need. Because look here, 8.33, the closest thing to it is 13. So definitely, yeah, we would choose 13. It cannot be 5 because 5 is way too small for it. It will not function. It needs a minimum of 8 amperes for it to function. And yeah, that's just pretty much all I have to say about this topic. We move on to question number 20. The switch shown below is deemed unsafe to be used in the shower room. Why? Because the water could go on the switch and it could cause an electric conduction, because water is a conductor of water, what did I just say? Because water is a conductor of electricity. Now, very simply, the electricity can flow through the switch due to water splashes because water is a conductor of electricity. Now, how can the situation be fixed? How could you prevent this from happening? What you could do, very simple thing, like what's happening in the UAE, what they did for the bathroom is they would put the light switch outside. So they will install the switch outside of the shower room. Or they will install a pull switch with a long cord of insulating material. So what's going to happen? If your hands are wet and you turned off the lights, okay, or you turned them on, you would use a pull switch. So it's like you pull it up and down, and it's made of an insulating material that would not let the current to pass through it. Or you could use a sensor switch that requires no hand touch. For example, you could use a switch that if you walk in, it will turn on. And yeah, that's pretty much all you need to know. Now, we move on to question number 21. A new domestic appliance includes a 5 ampere fuse. Choose the correct answers to complete the sentences below. The fuse protects the wire when there is too much current in the wire, because too much current might damage the device. A fuse is installed on the wire whose plastic case is colored brown. Why do we put it on the brown? We put it on the live wire because, as you can see, let me just open this. As you can see over here, these are the different types of wire. We have a live wire. We have the neutral wire, which is in blue, and then we have the earth wire, which is in green and yellow. So brown is live, neutral is blue, and earth it is green and yellow. Okay, and when the fuse blows it, okay, يعني when a current greater than 5 amperes crosses the fuse, what's gonna happen is that it disconnects the circuit. So it will cut the circuit or make the circuit open, so it will not flow and it will not damage the device. We move on to question number 22. Consider an electric diagram of a domestic appliance. Both ammeters show a current of 2.5 amperes. Since they are connected in parallel, we need to add them because in parallel the current is additive. So you add it, you are going to get a total of 5 amperes. So if you were to use a switch, okay, it needs to be a switch of 5 amperes. And always, sorry, by switch I meant fuse. My bad. If you were to use a fuse, you use a fuse of 5 amperes, okay? And always when you're using a fuse, you have to connect it in series with the switch. So this is our switch over here. You're supposed to connect it over here. Let's say this is the fuse, and it should be on the switch with what? With the live wire, not with the neutral wire. So very simply over here, it should be connected in series with a switch on the live wire, and it should have a fuse that is 5 amperes. Now a 20 ampere fuse was installed by mistake in its correct place. What would happen if the fuse, or what would happen if the circuit is switched on? If the circuit is switched on, very simply, nothing really is gonna happen, okay, except that if you were to put a current greater than 5 amperes, the device wouldn't be protected. So very simply, the fuse does not blow, but the circuit remains unprotected. So assuming the appliance is indeed safe to use, underline the symbol that is printed on it. If it is safe to use, it's supposed to be double insulated, or should have double insulation, so it will look something like this. Now we move on to the last question, which is question number 23. A house appliance is labeled 220 volts per 4 kilowatts and is protected by a correct fuse. The electrician of the appliance replaces the original fuse with a 5 ampere fuse. Is he supposed to do that? Let us see what happens. First of all, let us find the current I, or the current that he is supposed to be using in the fuse. So 4 kilowatts is 4,000 watts divided by 220. Very simply, 4,000 divided by 220, it is almost 18.2 amperes. So definitely a 5 ampere fuse is too little, okay? And because it is too little, it will cause the fuse to explode. So the fuse is gonna explode or blow, okay? So the fuse blows, however, the appliance is not damaged. So the fuse blows means that it will explode or the wire will cut and it will be an open circuit. This will leave the appliance undamaged, but again, the fuse is gonna explode. Now the lowest current label on a correct fuse that should be installed, we found it to be 18.2 amperes. So very simply, if you chose 20 amperes, which is the best option, then yes, it is correct, 20 amperes. We submit the quiz, so let us see if we have any mistakes. Thank God we don't have any mistakes. Thank you guys for watching. I hope you enjoyed and have a wonderful day. And before I do go, I would like to just do a summary of all the equations we have. So we have N2 over N1 is equal to V2 over V1 is equal to I1 over I2. This is for the transformers, okay? You only use this if it is 100% efficient or if it is an ideal transformer, okay? The next equation we have is, let us say, I'll just write it, peak value times sine of 2 pi frequency. Just remember it like this. This is how I will remember it. That means this number over here, it is the peak value, okay? And the number inside of the sine, which is usually multiplied by the time, it is equal to 2 times pi times the frequency. This is usually how I remember it. And then another is the electromagnetic force. It is equal to the inverse or the opposite of the magnetic flux over the change in time. And if they need the magnitude, you just put it in absolute value. And that is pretty much it. Thank you guys for watching. I hope you enjoyed and have a wonderful day.